Um, okay, so do you have any questions? Is there anything that in particular that you'd like to see? Um,
Can we do more practice on? So we are done with the A, B, C, D, right?
yeah, I am missing the second part of the group activity that we can do today. And I also like to talk about the multinomial theorem. There was only one problem on that in the wikis, but we didn't really go over it. And yeah, but other than that, yes, we're done with that. So, what would you like to see in particular?
More practice on, like lately that we've been doing it, like combination of like directly using the table that we have, like
Okay.
yeah, something like similar maybe.
Okay. Anybody
Something
else?
like it might be an exam basically. Complex one.
That's all right. Um, let's see what am I doing. So where am I? Oh, okay. So anybody else?
Yeah, Professor, I have a question.
Yeah.
Would you show me how to find the T number and S number just one more time on one example?
Yeah, sure. We'll go over that. So let me just write down because I start talking about something and then last time I forgot about finishing the class activity. So we'll finish the class activity. There's only the last part of the class activity, and then we'll go over the multinomial theorem, and then we can go a little bit more on some problems that use the table. And then we'll go over the computing T numbers and S numbers, or the Stirling numbers. Anything else?
Maybe not today, but for next class, can we do like a quick summary from part A to D, just to review before the midterm?
Okay, sure. We'll have a summary on Thursday. Okay. I have a question of the day. I think I opened it. Let me see. Did I open it? I think I did. So I have like the second question of the day. The first one was about, your background. If you've taken 366 before, it's just feedback, right? For today, the one that I opened for today, there's no time limit. Just please do it today. It's open. It's just, how comfortable you feel with each of the sections. Very comfortable to not at all. Just like a multiple choice question. And also the very last question in the it's called quiz because it has to, right? But it's not really a quiz. It's more of a survey. It's more like feedback for me. The last question is asking you to specifically tell me, like what you're doing right now, if there is anything that you'd like to see so that I can plan for Thursday, because I want it to be more of a review day. And so, but I need your feedback because there's a lot of material and I don't want to spend time on something that everybody knows and not have enough time for something that maybe all of you would like to see. So I don't promise that I will cover everything that you reply on that question of the day, but I'll prepare for it so that hopefully I can cover everybody's questions. All right. Anything else?
Just a quick question for the upcoming midterm. So is the like difficulties, or I would say the type of problems, are like wiki problems that we're expected to see on the midterm, or more of I would say class activities that we've been doing?
Yeah, I think it's going to be a mixture of the two, and I'll tell you more about on Thursday. You should definitely, to study for the exam, you should definitely go over the class activities that we had. Some of those problems are actually pretty hard. Some, as not all of them, because it's supposed to have a little bit of everything on that topic. But some of them are actually pretty hard. It's just that, in the wiki problems, they're kind of out of context, right? When we talk about the pizza problem, everything was related to pizza, and we had like the different variations. But some of those problems are hard. So my advice is go over all the class activities that we have, and also do your best to go over all the wikis. Remember that you are only responsible for a couple of problems, but all the solutions are there. And believe me, I spent hours, like hours. I just finished literally before I teach right before this period, and so literally right before my other class I finished, because I wanted you to have I wanted you to have everything ready. Now, if you see a problem, if you see something that doesn't make sense, please do let me know, because I've been going, I jump. It's a total of 80 problems for this week, 40 for me. But in a way, it's easier for me to just write all the solutions, right? Because I know what I'm doing and I just type them. But what I try to do is give you feedback, and I'm not trying to make anybody feel bad about it. When I say, "Oh, there's a problem here, there's a problem there," and the reason why I don't remove things, I leave them there, is because chances are that other people made the same mistake, and it's important for you to see, right? So that's why I do the wikis, because if I were to grade problems from everybody, let's say 10 problems from everybody, I cannot pay enough attention to the detail for each one of you. But if you identify something where there is a problem, you can see the feedback that I gave to other people, and you can also ask me if you see something else. Okay, so please do take advantage of those. Um, I know that it's a lot of problems, and probably you won't be able to go in detail over all of them. But my advice is try to do them. If you got the same answer, that's it. Just move on to the next one. But if you see something, or you don't even know how to approach a problem, then you should go over the solution and see. Okay. So that's how I will prepare for the exam. But I will tell you a little bit more about the exam on Thursday, the format and everything. I am considering, I really want to do it. I just don't know if I will have enough time to do it. But I want to have another quiz on distributions for this weekend. It's, the quizzes are more of a practice, because I cannot ask enough detail in the quizzes, but hopefully you will be able to identify areas where you need to study a little bit more or something. So I'm planning on that. I'll let you know on Thursday if I have enough time and to have it there for you. All right. So let me get started with this. Let me go to the group activity that we left behind. Where is it? We stop with the triangles. Where is my group activity? I lost it. Is it not here?
Professor, the quiz will be due on Sunday, right?
Yeah, well, here it is. Yeah, so we'll, so it's 8. Sorry, guys, I'll go back to 8. Here, found it. Yeah. So I'll have the quiz set for Sunday. Anytime you like to take it. Wasn't it? Yeah, here it is. Okay. So we went over the first part, but we didn't go over the second part, which is mostly about partitions. So, one more thing. If you, especially in the exam, my format for the exam is that everybody connects to the Zoom meeting, to the regular class. You don't need to have your cameras on or anything. But my reasoning, especially for this class, is that some problems are not extremely clear on, are the boxes here the same or different, or what's going on. So you can always ask those questions and I can clarify them. in real time for everybody. So you will be connected, and if you have any question, you let me know. And if I see something that's relevant to everybody, then I will open up my microphone and let everybody know. I in general try not to distract you because I know it's stressful. But if I see something, and then I'll let you know. Okay. So here, find the number of ways to distribute 8 identical balls into 4 boxes, and the conditions for the boxes are given in each of the parts. So we have identical balls into, let's see here, the boxes are identical, so identical into identical. Identical into identical, in general, is related to partitions of numbers, integer partitions or numerical partitions, because you just need to know. You just need to say how many balls into each box. But because the boxes are identical, it's just the parts, right? So this is usually related to numerical partitions. And here, no boxes are empty. So I'm supposed to use exactly the number of boxes that we have available. So this is just going to be partitions of 8, 4. Partitions of the number 8 into 4 parts. Now, we don't have a method, we don't have a formula to compute P84. What do I have red for? So we don't have a formula to compute P84, but we can find all of the partitions. So usually we do this by hand. So if you want to compute P84, it just means 4 parts. So you can start, I usually write them in increasing or decreasing order, one or the other, but in order, right? So I can do 1, 1, 1, and then I'm missing 5 to add up, maybe I'll add them as sums. 1 plus 1 plus 1 plus 5. So that's what I usually do. I start in increasing order only once only the last one is whatever it needs to be. And then I start breaking these. It's like the partitions of 6 into 2 parts. So 1 plus 1 plus 2 plus 4. So 2 plus 4 is 6. And another way to write the 6 is 3 plus 3. And then I increase the next number. So 1 plus 2 plus 2. So I keep using 2s until I get to the end. 2 plus 2, 4, and 1, 5. So this is 3. That's whatever I'm missing. And then I see if I can write this last sum in a different way, which I can't right now. I will need to add it once, but I don't want to, because those are already counted. The ones that use 2 ones or are already here. And then I increase the next number. So 2. And then I do 2s until, because it's a partition into 4, I use 3 2s, and then whatever I'm missing, I need to add up to 8. So that's that. And I cannot change anything anymore. So this is the best that I can do with 2s. And then I increase that number to 3. So now I will need to have 3 plus 3, only 3s, and it's going to be too much. I'm not allowed to use 2s anymore. So that's it. I cannot do anything else. So the number of partitions is, I just count 1, 2, 3, 4, 5. So these are 5 partitions.
Professor, can we use the Pascal triangle to find out the P84?
Yes, of course. With the Pascal-like triangle, you need to compute several rows, right, to get to that P84.
Right.
Yes, you can do it.
So we can use the Pascal triangle to find out the P84.
Yeah. And if you are using it, then let me know. So that's what I did in the wikis. If you look at more or less the comments that I have, I said, my advice for those who submitted problems by Thursday were something like, okay, so compute it, show how to compute it, not only the partitions, but the T numbers or the S numbers, or refer to a place where we can find them. So that could be the triangle, or you can show the triangle and then use it, or you can refer to a result in the book. For example, for partitions, when we created the Pascal-like triangle, we had that the partitions, we had that the partition of M into M parts. There's only one partition, which is the only ones, 1 plus 1 plus 1.
Mm.
And this into only one part, it's also 1, right? So those are
Right.
some, like a couple of small results that you can use without,
Right.
the initial conditions of the Pascal-like triangle. So you can just use them. Mhm.
I have another question. When we are making the partition, like you are doing 1 plus 1 plus 1
Mhm.
and plus 5, right?
Yeah,
So if I write 5 plus 1 plus 1 plus 1, those will be the same partition,
exactly. As partitions, the
so
same.
they are okay. So we cannot repeat this kind of order. It will be exact like the one thing. Like if I write 1 plus 5 plus 1 plus 1,
Yeah,
it will be the same partition. Do you understand
exactly.
my question?
And yes. In fact, the partitions are, so let me say, order of the terms in the sum is irrelevant. Okay, so in fact, the partitions are usually written as sets. Like 1, 1, 1, 5.
Right.
1, 2, 4. And written as sets, you can see that it doesn't matter if the 5 goes first or last or in the middle, right?
Mm.
So if you were asked to find all the partitions, like actually find them, you usually don't write them as sums. These are sets, right?
Mm.
Yeah. So I usually write them as sums because it's easier to make the connection that you're trying to add up to 8, right? But these are actually what we consider partitions. They are sets.
I have one question. Can you do a small number by using the partition Pascal triangle?
Yeah.
Okay.
Let me write it on my notes. That we'll get back to the Pascal-like triangles. Okay.
Okay. Thank you very much, Professor.
So remind me when I get back to my notes. Remind me to add Pascal-like triangles. Okay. So okay. So let's go to the next one. The boxes are identical, and at most one box is empty. So in the table, we have a spot specifically for this type of thing. So again, it's identical balls into identical boxes, so it's some kind of partition. This one says at most one box is empty. It means that we are either looking for partitions using exactly 4 terms, or because one box can be empty, we can use partitions into 3 parts. And then you can find all of them by hand or with the Pascal triangle. Let me just leave it there so that we can use the time for something else. The boxes are all different. So this time the boxes are different. The balls are identical. So if we go to our table, let me try to get the table exactly next to this. It's right here. Okay. So if you go to the table, remember, identical balls into different boxes. So this is my table. So we need identical balls into different boxes. That would be the first part. Different boxes are what we usually refer to as distributions. Although all of these are distributions, we refer to the bottom 2 as partitions. Partitions just means separate. It doesn't really matter into which container you put the objects. So that's why these are partitions. and everything above are not called partitions. So these are distributions, although the partitions are also distributions, but the book usually refers to these as distributions and these as partitions. So we have identical balls, which is this, identical balls into different boxes, right? And the problem says, so we're right here, and the problem says empty boxes are allowed. So we're right here. Identical balls into different boxes. Empty boxes are allowed. So it's just going to be this binomial. And this, when we first saw it, if you were to go back to the tables that we had at the beginning, we solved it by saying how many balls into box 1, how many balls into box 2, by solving an equation. Mm-hmm. So I'm just going to use this formula. So this is going to be, and then I'll explain the equation part. So here the m is equal to 8. The n, that's the number of balls, is equal to 4. And so my formula is m minus n minus 1 over n minus 1. So this one right here, n minus 1. M plus n minus 1 over, n, it could be over m or over n minus 1 because of that property of the binomials, the symmetric property. So I have 8 plus 4 minus 1 over 4 minus 1 in, or binomial of these, choose that. So this is 12, 11, choose 3. So that's using the table. And this was I don't remember changing to the other page. Let me have my printer copy in front of me so I can just tell you. So it would be 1, 2, third column, 1, 2, 3, 4, 5, 6. Column 3, row 6 of the distributions table. Okay? Now, if you don't like it, I don't like to use formulas just like that. So this is what you could do. You have 4 different boxes. So try to set up the problem and understand it, and you actually have the tools to solve it without the table. So I have different boxes that you can think that are different colors, and I have 8 identical balls. So I just, because I'm allowing empty boxes, then I can say how many balls go here, how many balls go there, how many balls go into box 3, how many balls go into box 4. I have a total of 8 balls, and all the xi's. So here, xi is the number of balls. And I just need the number, right? Because all the balls are identical. I just need to say how many. So the number of balls that go into box I. And because I'm allowing empty boxes, then the xi's are greater than or equal to 0. But you see, if I understand the problem this way, then I can solve any problem like this with other restrictions. So if instead of them telling me empty boxes allowed, they say there's need to be these many balls into that box and these many balls into that box, or there must be 3 boxes with this many balls and 1 box with this many, any of those conditions translates into conditions of the xi's. And we know how to solve a problem like that because we, before we started distributions, we learned how to solve all these types of equations, okay? So I think it's worth it to set it up like this, especially if there is a small variation of the problem. Like this one completely fits in the table, but others don't. So that's why I get this, right? Is the total 8, the number of separators is 3. So 8 plus 3, choose 3. Mhm. So it's this formula, the number of solutions to that equation.
Professor, yeah.
Yep.
How did you know the column equal to 3 and row is 6?
Oh, so let me go to the table.
Column
So,
3 and row 6.
yeah. So we first said that it is identical balls into different boxes, right?
Yeah.
And then we have no restrictions. So it's this one right here. So, I'm just kind of giving you the coordinates that you you can
I understand.
identify
I
or
understand.
think of later
Professor.
if you see your.
Thank you, Professor. I understand this part.
Okay. Good. All right. So the next one, the boxes are all different and no boxes are empty. So no boxes are empty. So you see, even without looking at my table, in this part, so for this one, my condition, is the same equation, but this time, because no boxes are empty, the xi's are greater than or equal to 1. Makes sense? And I know how to solve that equation. I just do, it's just going to be, I need to add up to 8, but I first put one ball in each box, right? So I already placed 4 of them. So it's the 8 minus 4, because I only need to solve my problem for the rest of the 4 balls. The number of separators is 3, and I choose 3. Mm-hmm. But, that's because I know how to solve these type of problems. But if you wanted to use the table, then you're going to need to, if it perfectly fits, it doesn't necessarily, it's not a guarantee for every problem. This one actually fits into a specific problem. It says no boxes are empty. So I can go to my table. And so again, identical into different and no empty boxes. So this one is this one right here. N minus 1, choose N minus 1. So that's same row and column 1, 2, 3, 4, 5. So, and in fact, let me write it like this. Look, this is 8 minus 1 over 4 minus 1. That's the m minus 1 over n minus 1 in column, what did I say, 5, I think? Row 6. So you can either use the table directly, which is this over here, or you can use solutions to this equation, which I wrote first here. I need to add up to 8, but 4 of those balls are essentially fixed. So I take care of those first. So that's why I'm subtracting the 4, and then my 3 separators choose 3.
When we're testing, are we supposed to explain all that, or we are able to just write the straight away?
I'm gonna allow to use the table in the exam. So if you decide to use the table with not a lot more explanation, then that's fine. But that's why you need to tell me what in the table you're using and why. So in this case, you will need to say, okay, I have identical balls into different boxes with this restriction, which perfectly fits column 5, row 6 of the table. And then you can simply substitute. If you're not able to fit it, or if you slightly, if you need to make a modification, then explain what modification you're doing. And I'll explain more on Thursday. But for some of the problems, I do want you to compute an exact value because, that's part of the understanding of these symbols. But for many, I might have problems where I just need you to say something like this so that you don't spend time on the computation. But I will be clear when and when. Okay?
Okay. Thank you.
All right. So, and finally this one. There is let me see which wiki. There's a wiki that has, I try to separate the problems in the wikis more or less by topic. And so there's one section in the wikis that, one wiki that contains several problems that are like this. The third one here. No. I don't know which wiki it is. Let me see if I find it. I don't know, anybody remembers a problem where I asked to prove some divisibility property? I don't know, I'll find it. But I think I put all the proofs of divisibility proofs together. In fact, I think it was something C or D 37 and then 60s, 67, 68, something like that. So all of those are very similar to this one. Combinatorics is pretty useful and sometimes surprisingly useful. And this is one of those types of problems. Prove that for any positive integer n, the number n to the cube n cube factorial is divisible by this one over here. And so the idea for this type of problem is that you could find a problem or an expression that's equal to the quotient of these two. You take one and divide it by the other. You're trying to prove that they're divisible, so you're trying to prove that that's an integer. So you're trying to prove that, let's see, let me first write it down here. So prove that any positive integer n, for any positive integer n, then this number is divisible by this one. So you're trying to prove that this one divided by that one right is an integer. That's what we're trying to do. So that 8 is divisible by 2 because 8 over 2 is an integer, 4. So we're trying to prove that this number divided by that number is actually an integer, or this second number goes evenly into the first one. So this is what we're trying to prove. So if we can show that this is the solution to a counting problem, then it has to be an integer. So, but we need to come up with a problem that has that solution. So I'm gonna say here, it is enough to find a counting problem with this solution, right? Any counting problem will have an integer solution. So that's the idea. It doesn't have to be a counting problem. It could also be, if it happens to be a binomial or a multinomial or something like that, we know that those things count stuff and therefore they're integers. A T number, an S number, anything like that. Okay? So that's what we want to do. Let me move this to a different page because it's getting very crowded. So I'm just going to copy this. I'm just going to paste it here. Okay? So what counting problem can this be? Let's see. I have this n cube factorial. So I'm thinking, okay, maybe because I have the n3 factorial on top of my denominator. So I'm just going to say these are my tries, okay? So because I have that there, maybe I should be considering a multinomial or a binomial that uses n cube on top, right? Because the multinomial coefficients will have that n cube factorial divided by something. Okay, and then, I copied something wrong. Oh no, this is okay. And then, let's see. I have these, n square factorial. Okay, so maybe I can try having n square, as part of my multinomial. Or maybe if this is I also have n factorial to the n square, so maybe I can have n's, this again, I'm just trying. So maybe I can have several n's here, because I'm not saying how many, right? But if I had something like this is just a try, remember? So instead of me giving you just the answer, this is just a try. This looks like this. So if I have, I don't know, A of them, then this will be A of them. And so this is factorial. So this will look like n cubed factorial divided by n factorial to the A. And in my solution, I have, but I need to have, in the multinomial, I need to have these numbers. I need to have these numbers to add up to n cubed. So I need to have, in order for this to work, or to be well defined, I need n plus n plus n a times to be equal to n cubed. All right, my multinomials are defined that way. The numbers in the bottom need to add up to the top. And so the A has to be n squared. So this one is actually n cubed factorial divided by n factorial to the n squared. So I have part of my expression, so maybe I can use this multinomial. I actually have this part of the expression. Not that one. This one right here. And now I just need to divide by n squared factorial. So I have a multinomial. That's divided by a factorial. And it actually happens to be the factorial of the number of n's that I have here. Okay? So look, I have a multinomial. That's this shaded part is what I just got here. I have a multinomial that's divided by a factorial. I'm going to actually look into my distributions table and see if I can find something that looks like this. So it's a multinomial. It's that shaded region. That shaded part of my expression is a multinomial. So right now, what we need is this n cubed and this is n squared times divided by n squared factorial. We need to check that that's an integer. So I'm going to see in my distribution tables if there is something that looks like this. Or if you can come up with a problem, that has a solution that looks like this. So let me go to the distribution table. Remember, it's a multinomial divided by a factorial.
That's t, right?
Which one?
T. Yeah, s over t, so something like that we can make.
Something like that, right? So here I have divided by n factorial, but this is a t number, and I actually don't have a t number. I have more of a multinomial coefficient, so something like this. That's divided by a factorial, but here I have many factorials, but it looks pretty much like this one, right? Let me zoom in. So it looks a lot like this one. It's just that I have a single factorial on the bottom. So, but if you remember about this ones, we're dividing by the multiplicities. So this is like we had, when we had problems like, I don't know if, so these are eyes are just the multiplicities of the, how many of these m's are equal. If I have R1 m's that are equal, then I divide by R1 factorial. Anyways, it fits this one as long as I only have one multiplicity. Let me zoom out. So this type of binomial, the multinomial is like this. For example, 10 choose 3 3 2 2, or maybe I should do 3 3 4 4 4. Oh, no. Sorry, not 10 then. So 3 plus 3, 6, 10, 18. For example, if I have something like this, the r's, the r's in this expression are just the multiplicities. So I have 2 of these and I have 3 of these. So what that part is saying is that you have to divide by 2 factorial, 3 factorial. Those are the multiplicities. Mm-hmm. So if all my m's were the same, so for example, if I had 18, 3, 3, 3, 3, 3, 3, the I factorial that I need to divide by is, because I have 6 of these here, I have to do 1 over 6 factorial. And that looks like what I was trying to do. So I need to create a problem that has the solution where all the m's are the same. Okay? So where all the m's are the same. Now let's see what problem is that. So this is different people, or different balls into identical boxes. So like different people into groups. Number of ways to distribute the number on top of people into identical groups, so that my condition here is this one right here. Is the number of specified numbers of balls per box. And I'm saying that all of them have to be equal, right? I'm saying that all of them have to be equal. And in fact, let me bring my the expression that I wanted, right? I'm just gonna copy it so that you can compare. So this is what I want. So again, we need the number of top is the number of people. So I need n cubed people to go into the number of identical groups. That would be the number of boxes. And if you look at this formula, that's the n. The sum, the MIs is how many balls into the number of boxes. Oh, sorry, here in my formula, the n is the number of boxes, so it's the number of terms here. So my number of boxes here is the number of terms here. The number of numbers in the bottom part is n squared. So this has to be n squared boxes. And not boxes, I'm just going to say rooms, right? So these are different balls into into groups, sorry, into identical. And the MIs are the number of people in each room. So that there are n people per room. Mm-hmm. And the solution is going to be this one right here. Mm-hmm. So now we fit that into our table. We realize that it might be related to this. We see what numbers we will need to use to actually get this expression, and then see if we find a problem that, any interpretation. Like I gave you some suggestions in the table. Oops. The suggestions in my table are like this, number of different balls you can replace by people, identical boxes you can replace by groups. So this is my problem. Mm-hmm. So the solution now for that part 3 is, I'm sorry guys, this is just, okay. So I'm gonna bring this over to the other page. So this is what I need. Yeah, okay. So this is what I need. Mm-hmm. My problem is find, or actually I'll say the number of distributions into n, or the number of ways to distribute n-cube people into n-square groups. Maybe I'll actually say it that way, number of ways I'll say it like this. Number of ways to separate n-cube people into, or to break n-cube people into n-square groups is equal to that formula. So I take the n-cube people and I have to decide how many, so that there are exactly n people per room. So I take the n-cube people and I say, I choose n to go in the first room. I choose another n to go into the second room. I made a mistake here. Group. If I actually had rooms, this is how I will answer my question, right? If I had rooms, this is the definition of the multinomial. I have n-cube people and I choose n to go in one room, n to go into the second room, n to go into the next room, and so on. So I have n square of those here. But because there are no rooms, I'm just making groups. Then it's as if all the rooms were identical. So I need to divide by all the permutations of the people. It's the same if I say you're group 1, group 2, group 3, as saying, oh, no, you're going to be group 2, group 1, group 3. All the permutations are counted more than they should. So that's why I need to divide by this. And therefore, this is an integer. So this is the answer to the problem. No? That's it. So maybe I should say this is equal to what they gave us, n cube factorial over n factorial to the n square times n square factorial. Okay? Questions? Okay, so finding this, I could have told you, let's count these and check that this is actually the answer by fitting it, by checking what I should do in my table, and then find the answer and notice that this is exactly equal to that. I could have done that and we could have spent a third of the time that I did or less. But I wanted to tell you how you could find this problem that gives you that solution, because we're finding the problem. We have the solution, but we're finding the problem. Okay? Now, if you want to settle for that, at least for now, just, answer this question using the table. So I have number of ways to separate n cubed people, or to break, maybe I should say. It sounds better. To break a group of n cubed people into n squared groups, right? So we're just making groups. This is different balls into identical boxes. And so there is the condition that we are specify exactly how many people per group. So you can go to your table, you have different balls, so people here, into identical groups, and you have a specified number of balls here, a specified number of balls per box, which is n per group, right? And so you can just see what it is this one, and you need to understand what this means. This means the total number of people goes on top. How many per group is listed here? So it will be n, comma, n, comma, n, comma, n, and so on. And the r's, well, this first part just says that the sum of the n's equals the total, which is fine, that we have as a given in the problem because we're distributing all the people. And the ri, what this means is the number of subindices, so the number of elements in this list that are equal to I. So in my case, all the numbers are equal to n. Those are just the multiplicities. So because all of them are equal to n, then I need to divide by the factorial of how many I have, which is the n squared factorial. So these are just the multiplicities. That's what that means. And as I show you here, in a case like this could be like 18 people into 6 groups of the same size, right? So I have 18 people, 6 groups of the same size, that would be 3 each. So I need to select 18 to go into one room. Then the 3 that go into the first room, the 3 that go into the second room, and so on. But because these are not rooms, these are groups of people, there is no order, so I need to divide by their multiplicity, which is 6 of them, so I divide by 6 factorial. 6 of them are equal. Okay? Questions? Okay. Okay, let's see. What was my next thing to do? And then I told you, remind me to go to the Pascal, back to the Pascal-like triangles. Oh, the multinomial theorem. Let me do that one because that one is fast. So the multinomial theorem is like the binomial theorem, but for more. The binomial theorem is because you have binomials, right? So 2 terms in your polynomial. For this one is any number of terms. So you can have x1 plus x2 plus, let me see. Let's do it like this. Plus xn. I like to keep the same notation that will go well with the table because I always get it backwards, but it doesn't matter. So if I have something like this, let's see, let me write the binomial theorem. The binomial theorem just says that this is equal to the sum from k equals 0 to n of n choose k, x to the k, y to the n minus k, right? The reason we do this is because we need to select x's or y's from each of the parentheses, each of the factors. that we're multiplying right here, right? So these two numbers, the exponents, need to add up to n. So the same thing is going to happen here. You have n factors, and from each one of them, when you expand, you're gonna choose one of the xi's from the first parenthesis, another from the second parenthesis, one more from the third parenthesis, and you can repeat. So all my terms are going to have the form x1 to the m1, x2 to the m2, and so on. xm, oops, maybe I shouldn't call them m1 and 2. Maybe I'll call them differently. So instead of m1 and 2, I'm going to use a1, a2, am, right? So all my terms look like that, but the sum of my exponents is going to be the total, which is the n. I have n factors, and I'm just taking one x from each one, and so the total needs to be n. And the coefficient is just going to be n choose a 1. Oh, I know what I'm going to use nx. Sorry, guys. Let's do this. I think it's going to look much better. So n1, n2, nm are my exponents. The sum of the exponents equals n, and my coefficient is just that. And these are integers that are greater than or equal to 0. And so, as you can see, just note that in order to go from the multinomial to the binomial theorem, n choose k can also be written as n choose k n minus k, as a multinomial. So the n choose k is actually like a shortcut for this. This is just the n factorial divided by k factorial and minus k factorial, right? So n choose k is like the shortcut for the multinomial coefficient with two terms on the bottom. And so this formula becomes the same as that one, This formula, x plus y to the n equals, you could do the sum over n1, the pairs n1 plus n2 equals n, where all the ni's are greater than or equal to 0 are integers. And now you have the n choose n1 comma n2, x to the n1, y to the n2. So it really is the same as this one. You're just fixing, the value for your first one, the value for your first one, all the possibilities, that would be the k, and then n2 is going to be n minus that k, because the n1 plus n2 is n. So it really is the same. You can write it like this. n1 greater than or equal to 0, and choose n1 comma n minus n1, x to the n1, y to the n minus n2. Or maybe, I know how you can do it. Yeah. So from here to here, I'm going to make k equals n1, and n1 plus n2 equals n, implies n2 equals n minus k. So now I can actually replace each of these n1s by k's. And it actually looks like my binomial theorem. So the binomial theorem is just a special case of the multinomial theorem. So, for example, I can ask you for the coefficient of x cubed plus x cubed plus y to the 4 times z squared in the expansion of x plus y plus z to the 9. And this is a 2. Okay. So according to the multinomial theorem, the term that corresponds to x cubed y to the 4 z squared will have so x cubed y to the 4 z squared has the coefficient 9, choose 3, 4, 2. So the coefficient is just that. And I wrote it like that because I'll just leave it like that. It's 9 factorial over 3 factorial, 2 factorial, 4 factorial, 2 factorial. But then, same as we did with the binomial theorem, it's the same idea, just now we have multinomials, right? So you can have things like maybe you have x, and maybe you have, or let's say maybe you have 5x, y squared minus 8 to the 9. Same question. So this time we need to first understand which term we want, and then combine all the constants that will make up the coefficient. So let's see. So I need to have an x cubed. So I need to have 5x cubed. And then I need to have a y to the 4. So I need to have a y square. That will give me the y to the 4. And then I also know that the sum of the coefficients needs to be 9. So I have 3 plus 2 plus the last coefficient needs to be 9. That's the coefficient the last exponent. That's the exponent that goes there. So 3 plus 2, 5. I'm missing 4. So I need the exponent 4 there. And I need the negative 8 there. And now that I have the exponents, I also have the multinomial 9, 3, 2, 4. And so the coefficient is 9, choose 3, 2, 4, 5 cubed, negative 1 to the 4th. So that's my coefficient. So this problem should be easy. Yeah, go ahead.
Professor, so in the exam, do we need to compute the value of those, or just itself it's okay?
No, just leave them like that. The computations to actually get to a whole number are mostly, I'm going to ask you for those mostly for the T numbers, S numbers, or the partition numbers, because we're learning how to compute them, right? They're new to us. But these ones you can leave like that. But again, I'll be explicit what to compute and what not to compute, so that you don't spend time on something that's not necessary.
Professor?
Yeah?
What about that z squared part?
Which one?
X to the cube, y to the 4th, and z squared. But I only see in the expansion of the term.
Thank you. Okay, yeah, you're right. I was making up my example. So let me say that we are looking for, um, so in this one, let me fix my problem. Find the coefficient. Thank you. Thank you for noticing that. I was making up the problem on the spot. So find the coefficient of x cubed y to the fourth. Yeah, there is no z, right? So the coefficient will be 0.
Okay, because yeah, I noticed in part A you matched it where it was the x cubed and the y to the fourth,
Yeah.
y squared, and then square that, which made
Yeah.
it y to the fourth, but then negative
Yeah.
8 to the fourth. So I know how you got negative 8 to the fourth, but I wanted to make sure.
Yeah. No,
that
you're right.
also was
The problem, well, it makes sense, but it would be silly to ask you because then the coefficient will be 0. There is no z, right? But thank you. And actually, let me say this is part A and that's part B because I'm looking for a different term, right? Yeah, thank you. Okay, so let's see. So we did a little bit of distributions table, but we're going to do a lot more next time. Comparing T numbers and S numbers. Okay. So,
and how did you reduce negative 8 to just negative 1?
well, I don't know what I'm doing, Sean. Thank you. That's a negative 8. I got all mixed up with the Z and the 8. Okay. I decided to put the 8 last minute because I knew I couldn't get the Z square unless I had like radical Z, right? Yeah. Anyways, so computing T and S numbers. You can use your triangles, but also the easiest way is to use that dot product that we used before. So, for example, if you want to compute, I don't know, let's say T of 10, 5. Okay? So you're supposed to have, we're going to have the dot product of two vectors. So this is going to be the fifth row of the usual Pascal's triangle. And this is going to be powers of 5, 4, 3, 2, 1, 0 to the 10th. Alternating signs. So the fifth row of Pascal's triangle So this is the fourth one and then the fifth one, right? So that's what I'm going to have here. 1, 5, 10, 10, 5, 1. And then I should have the same number of entries. So, 5, 4, 3, 2, 1, 0. All of those have exponent the other number. And then I alternate signs. Okay? Makes sense? And if you doubt it, like the place where I always have to think a little bit is what's the exponent and what am I reducing, right? 5, 4, 3, 2, 1. And so it's easy because I need to have exactly the same number of entries here than there. So here I have 6 entries. It wouldn't work with 10, 9, 8, 7, so on, right? So it has to be the 5, and the other one is the exponent. That's how I deal with it. My secret. All right? So I always forget which one is which, so I have to think a little bit. All right? And then just multiply entry by entry, right? So now you multiply first times the first one, second times the second one, third times the third, and so on. So now you have 1 times 5 to the 10 minus 5 times 4 to the 10 plus 10 times 3 to the 10 minus 10 times 2 to the 10 plus 5, and the last one is always 0. All right? Good. Now, this S number. Once you have this one, the corresponding S number is just the T number. Oops. So the T number divided by 5 factorial, right? So just whatever you got before, divided by 5 factorial. Now, this will be okay for me as a computation for the T number in the exam. I know that this is still not like a final whole number, but let's say if you can do it with a very, very, very basic calculator, products, exponents, the factorial, then that's fine. Okay?
By basic, do you mean not use the TI-84 plus calculator?
Basically, you're not allowed to ask for the T number, right? You're not allowed to ask for a dot product. You're not allowed to use for,
it's because I know how to use the summation thing. It's a math key, and then they press 0, and then I just enter in the summation.
That's fine. I mean, if you wanna keep going and get that integer, that's fine. It's just gonna take a little bit more time, right? And in the exam, maybe you don't want to. But
it's definitely a little bit easier than trying to enter in 5 to the 10th minus.
Oh yeah, 5. definitely. But what I mean is, if I ask you to compute the T number, don't tell me just the answer is T10.5, right? Tell me this will be the answer, because this. Let's say if I
could leave it like that, then that's easier for me. I don't need to use a calculator.
Just leave it like this. You see this you can do with an extremely basic calculator. It's just products, sums, subtractions, division.
Right.
Okay?
And on the quiz, you might want to evaluate to a value, like a single value.
Yeah, in the quiz, I'm sorry guys, but yes, just use any calculator you want, because otherwise, if I want to do it electronic so that I don't grade it and I rather spend the time on the wikis and all that, then I have to do it so that you get down to a whole number. Okay?
Professor, in the exam, we have to calculate all of them, or we have to leave like that?
I'll be precise. If I ask you to compute, I mean that you could leave it like this, as long as it's only sums, differences, multiplication, division, then that's fine. You can just leave it like this. But in some problems, you could leave your answer as T10.5, but that's what I will make precise, okay?
Okay.
So,
but I'm fine with T and S, but right now I'm looking for P. Partition. P. P with Pascal triangles.
Yeah. So, okay. So what am I missing? I'm missing the Pascal-like triangles, and we'll use the table a lot more next time, and then the summary. Yes. So where are my Pascal triangles? Okay. So what I'll do for you is we can do this a little bit more next time. So this is the regular one. What I'll do before I upload the notes, because time is over, I will complete this once, okay? I will make my markings of what's going on here. Just remember for the T numbers triangle, it works almost the same as the usual Pascal triangle, but you need to multiply, it's the sum, and then multiply times the second entry. Sum, second entry. Sum times the second entry. So if you already have 2 of them, like this one, I can already do. So it's 36 plus 24. That will be the usual, right? But then I need to multiply times that second entry. Okay? So the T numbers triangle, it's, I think, the easiest of, besides the usual. The S number, so the important thing is to remember this rule, and of course the initial conditions. The S numbers triangle, the S numbers triangle, I feel it's a little bit harder, but not as much, It's also like what I have in black is what you will have in the usual, just the sum of those two numbers. But the second entry only is multiplied times that. Times that 2 or times these 3 here. So if I were to do this one, then I will have 6 plus 4, 1, oops, 6 plus 1, the sum of the two above. The only extra thing is I need to multiply times that entry. So the multiplication is for the entire thing in the T numbers and only for the second term in the S numbers. Yeah? So it's this formula here. The extra N only goes with the second number. In the T numbers is for the whole thing, right? And so the only ones that are harder are the partition numbers. Okay? I'll complete this at the beginning of next class with you. All right?
So is the quiz this week, you said?
Yeah, for the weekend, after Thursday. So it won't be open before Thursday. Because if I actually do it, if I have it ready, I'll let you know on Thursday. Okay, but it won't be open before.
And then the exam's on Tuesday, right?
The exam is on Tuesday. Yeah, the quiz is part of your studying for the exam. All right?
Professor, quiz will be based on C or D or A, B, C, D, all of them.
A or B. What are you talking about? The sections of the book?
Yeah. I'm asking.
Yeah.
For the quiz will be...
The exam is sections A, B, C, D.
My question is on the Thursday, the quiz will be for only C or D or A, B, C, D.
Well, C and D distributions.
Okay. Thank you, Professor. Thank you very much.
All right. You're welcome.
I have a little confusion about the P with Pascal triangle. So you are doing this one in the next class.
Yeah, I'll do this. I'll complete this with you next time.
Okay.
The rule is a little harder, but the numbers are pretty small.
Yeah.
Here. Okay. So all right. Anything
Thank
else,
you, Professor.
guys?
Thank you very much.
No problem. I'll see you next time.
Thank you, Professor.
No problem, Noah. Oh, I thought you had. Did you have your vaccine?
I did. For the first few minutes, I was in my car listening for the first few minutes, but then I got home around like 15 minutes in, and then I joined regularly.
Okay, good. I'm glad that you got it.
Got my bandage on my arm.
Yeah, I got it on Saturday, so I'm super happy. Yeah. All right, guys. Thank you so much. I'm glad, Noah.
Professor, I had a question.
But I'll take a look. I think in class today, but I'll check if there's anything else. Yeah.